We had just started this the other day. You bet. Thank you. We're going to spend the next couple days talking about electrochemical cells. And basically, we defined electrochemical cells as or involving a chemical reaction and a flow of electrons. And so basically, all electrochemical cells undergo good old redox reactions. Okay? So when we're talking here about electrochemical cells, there's two types, but both are going to involve the redox reactions. And we had just gotten to this part right here where there are two types. We have the first one, which is called a voltaic, also sometimes called a galvanic cell. Means the same thing. And these involve spontaneous redox reactions that produce
Sorry for the interruption. Any students who are supposed to be going on the honor
a
merit
flow of
field trip today,
electrons.
if you have not turned in your permission slip yet, please do so immediately to Mr. Wager in the main office. Otherwise, you will not be able to go. Again, any students who are supposed to be going on the honor merit bowl field trip today, if you have not turned in your permission slip yet, please do so immediately. Otherwise, you will not be able to go.
What does the term spontaneous mean? Good. It doesn't need a continual input of energy, which we would say is like a driving force. So this spontaneous means it basically happens on its own or without a continuous input of energy. Tell me a process that you know is spontaneous. Combustion. Good. You start something on fire and you don't have to continually hold a match to it. A few weeks ago in here. I think you're right. I think I remember what you're saying. Basically, if you have any reaction that gets you over that activation energy, it will go on its own. Yes, entropy. So I had given the example of if you are, for example, standing, up on a mountain and you have a boulder, and you just give this a little bit of a shove. Once you get it over that initial input, it'll just roll on its own. Gravity takes over. That's a spontaneous process. So these batteries, these guys involve a spontaneous flow of electrons, and that will occur until you have a dead battery. And then the flow of electrons stop. If they're non-rechargeable, the battery is useless. If it's rechargeable, then you can recharge it to then get another useful energy expenditure from it. But it's important to know that these produce electricity, and the other type, which is called an electrolytic cell, these require an electrical current to force a non-spontaneous reaction to occur. So these guys require an electric current to force a non-spontaneous reaction to occur. Now, Kaylee had said her dad used to work at Jamestown Electroplating. And when we get into electrolytic cells, we will look at this process of electroplating. Some of you who are into cars might know that a lot of your really fancy cars have what type of bumpers? What type of metal on, like usually the fronts, the grills? Motorcycles oftentimes are kind of decked out with something plated metal. Chrome. Yeah. Your chrome is really, really shiny, all right? And those bumpers are what's called chrome electroplated, and they are plated so that just a thin layer of chrome goes onto a cheaper metal, such as iron, and it gives them a really cool look. But a lot of your silverware is also electroplated. So how many of you eat off of pure silver? Sophia? Anyone else? I don't even think I have, like, pure, like, I was trying to think if I have anything made of pure silver, and I'm not sure. I don't think I do. So you do have actually a set of pure silverware?
Yeah, but my grandma will like stab you with it.
Touch it. Yeah.
Why do people buy that?
I don't
They just like
Most people just inherit it.
just sits.
And who's gonna be impressed by this?
Okay, I have a question. Wait.
Yeah.
I
don't know.
Like twice.
What's that, Madison?
My grandma has these plates and it has like gold around the outside. And one time I put it in the microwave and it started like sparking.
Any metal in a microwave will cause electrons to be ejected and spark.
And she yelled at me.
Here we go. Voltaic cells. We're going to take a good look today at the first one. We know these require or produce electricity because they use spontaneous metal reactions. They consist of two pieces of metal called electrodes. Two pieces of metal that are called electrodes. And these guys are basically going to be the sites where oxidation and reduction occur. One of them is called the anode. And at the anode, this is where you're going to have oxidation occurring. The other is called the cathode. And this is the site where we're going to have reduction occurring. Now, I've mentioned the new memory ditty a couple times. Does anyone remember how you remember this? Anox, red cap. You got it. Anox, red cap. The other thing to keep in mind is that batteries have these electrodes, and the other way that sometimes you'll hear people talk about electrodes are terminals. And the electrodes on a battery have what signs associated with them? Positive and negative. Do you know, Sophia, which one is considered positive out of these? I was going to say most people wouldn't just know, but the cathode is your positive terminal of the battery or positive electrodes. The way I remember it is in cathode, you have a plus sign with the T. Yes.
I remember this.
An anion is negative, and so your anode, good way to remember it. I just remember a cathode positive, but yeah, I like that too. You can remember anion is negative. Okay. There's a few other things that take place in these voltaic cells. You have to have something that is called a salt bridge. For those people in lab, can anyone remember the purpose of the salt bridge? It completes the circuit. Very good. Completes the circuit by transporting ions through solution. Very good. That is the purpose of the salt bridge. Another way to say that is this: it prevents what buildup? Charge buildup. Very good, Mitch. So the other way you can say this is that it prevents charge buildup. And remember, electrons will always want to flow from a higher reactive metal to a lower reactive metal. Electrons will want to flow from a higher reactive metal to a lower reactive metal. The best way now is to put this together with a picture. So here's what it looks like. people in lab, this is going to look really familiar. The first thing we do is we have two beakers. We are going to place into the beaker on the left an electrode made of zinc, and on the beaker on the right, an electrode made of copper, Cu. Now, the first thing we need to do is determine which one of these is going to act as the anode. And if you remember, the anode is the metal where on table J? Very good. Anode is always going to be the higher metal on table J. So, can anyone remember which one's higher? Absolutely, zinc is higher. We generally put the anode on the left-hand side and the cathode on the right-hand side of these drawings. We are going to take and connect these pieces of wire connect these two electrodes with a piece of wire, and that provides a pathway for the flow of electrons. And what we generally do is put in here some type of device called either an ammeter or a voltmeter to measure either the current flow, that's what an ammeter does, is measures how much the current is flowing, or a voltmeter, which measures voltage. But please recognize, this is not a battery. The whole system is basically making a battery. A voltaic cell is a battery. This is not doing anything in terms of helping this system to work. You can take the ammeter out, and it'll still keep working. All that does is show you the measure of how much current or voltage you have occurring. Now, electrons want to flow from zinc to copper, but you know from your knowledge of electricity that electrons cannot flow unless the circuit is complete. So if this was all there was in the cell, you would get maybe an initial zap of electricity, like when you chew on tinfoil, and then it would be over. And the reason is because when the electrons get over to the zinc, go from the zinc to the copper, they can't complete themselves. Question? Sorry? That's exactly right. So we've got to finish this by doing a couple things. First of all, we've got to have some ions in this cell. So in this particular cell, we're going to put zinc sulfate, and over here we'll put copper sulfate. And then we've got to have a way for charge to get from the copper back to the zinc compartment. But we've got a problem. And that problem is electrons, which have now come onto the copper. These are full of electrons now that have flown through the wire to the copper. Electrons cannot travel through a solution. Electrons never travel through solutions, only through what? Metals. They can only travel through wire. What is going to take the charge back to this side? What type of particle carries charge in solution? What? You're right. Ions. Yeah. So what happens here is you have another ditty. Caleb, keep your hands to yourself. Ions travel where? Anode. Ions to the anode. Cations travel to the cathode. Now, what do I mean by anions and cations? We are going to take, and in this salt bridge, we are going to pack it full of something like sodium nitrate or sodium chloride. We're going to take a salt and fill that salt bridge with a salt, and we're going to plug the ends of it with a porous type of compound. In lab, we're going to use basically a cotton ball. But this still allows ion migration. Now, the first thing you have to do is recognize that the salt, the NaNO3, is going to dissociate. Someone please break that apart for me. Na plus, NO3 negative. Good job. Which one of those is the anion? The NO3. The negative ion is the anion. There is your anion. Which one is the cation? Here is your cation. Tell me, which way is the Na going to flow in this salt bridge? It's going to flow to the right because the cation is going to go toward the cathode compartment. Which way is the nitrate going to flow? To the left into what is called the anion compartment. Now what happens, you'll notice, is that the electrons go all the way across to the copper, and now we've got to get negative charge going back to this side, and so the negative NO3 negative does that, and it takes the negative charge back to where it came from. It does what to the circuit? Completes it. You'll also notice that in this side, we have Na plus going in. Now there's a reason there, or for why that's occurring. The Na plus has to replace some positive ions that are being lost. Anyone remember why positive ions are being lost in the cathode? We have two half reactions that are occurring. Yes, they are. In the cathode, we have copper ions that are bumping into the cathode, picking up electrons, and forming what? Finish that reaction. Cu. Very good. That means that this entire electrode is actually getting larger. The copper electrode is building more copper as the ions are going out of solution, meeting the electrons and plating copper right along and building that electrode. What's happening in the anode compartment? Someone write the half reaction. Zinc yields Zn plus 2 plus, very good. Can anyone tell me what's going to happen to the zinc electrode in terms of size? It's going to get smaller. The zinc is actually dissolving into zinc ions, and it's producing the two electrons that are coming across the wire and down into the copper. This is why it's called a spontaneous redox reaction, because you're providing a pathway from electrons to go from an active metal to a lower active metal spontaneously. And this cell produces 1.10 volts. It's almost equivalent to your AA and AAA, which produce 1.5 volts. This was one of the first batteries called a dendritic cell that was produced to basically harness electrical energy. Huge, huge, huge deal. Okay, someone tell me, please, the full reaction that occurs. Okay, Zn plus Cu plus 2 yields Zn plus 2 plus Cu. That is the overall reaction that is occurring in that cell. Overall reaction that is occurring in that cell. Okay, what I want you to do, remember, by the way, by convention, the cathode is the positive and the negative is the anode compartment. I want you to draw a voltaic cell using this setup. Iron, iron ion, and we're going to use, this time, silver, silver ion. The solution here will be iron nitrate. The solution here will be silver nitrate. And in the salt bridge, you can use just NaCl. Using the model that we just created, I want you to draw a full galvanic cell that uses these electrodes, label all the parts, and write the half reactions that occur on each part. Make sense? Go to it. When you're done, check it with mine.
Sorry for the interruption. Would all 5th and 6th grade students who are going on the Honor Merit Roll field trip please proceed to bus 103 now? Again, all 5th and 6th grade Honor Merit Roll students that are going on the field trip today, please go to bus 103 now. Thank you.
All right, I'm coming around to help you out if you're stuck.